Imagine peering into a pitch-black cosmic void, realizing your entire world is nothing more than an invisible speck of dust floating in an endless ocean. It is a chilling realization that shakes the very core of human identity. Every triumph, every civilization, and every war ever fought happened on a microscopic rock spinning through an indifferent abyss. We live out our lives completely unaware of the mind-boggling scale of the cosmos that surrounds us. It is time to peel back the curtain of our daily lives and face the staggering reality of our true size in the universe. Prepare yourself, because once you see the cosmic scale, your perception of reality will be permanently altered. Our journey of perspective begins right where you are standing right now. To a human being, the Earth feels absolutely massive, a permanent and unshakable foundation. If you look out at the horizon, the world seems to stretch on forever into the distance. We measure our journeys in miles or kilometers, and a trip across an entire ocean feels like a massive undertaking that requires hours of jet travel. The highest mountains, like Mount Everest, pierce the sky and feel like the ultimate symbols of size and grandeur. The deep oceans drop down into dark abysses that human eyes rarely ever get to glimpse. This is the world we know, the setting for all of human history and experience. Yet, this massive planet of ours is just the baseline, the absolute smallest unit of measure when we start looking upward. When you step off the surface of the Earth and look back, the scale immediately begins to shift in a dramatic way. Our home planet is actually a very fragile, isolated oasis in a vast desert of empty space. To understand just how small we are, we have to start comparing our home to its immediate neighbours. When placed next to the truly giant bodies in our solar system, the Earth quickly starts to lose its status as a massive entity. It becomes a tiny marble in a playground filled with much larger objects. Let us first consider our own moon, which looks quite large and luminous in the night sky. The moon is roughly 1/4 the diameter of the Earth, which makes it quite big compared to other moons relative to their planets. But the distance between the Earth and the moon is the first real hint of cosmic emptiness. It sits about 239,000 miles away from us. That distance sounds manageable, but it is actually wide enough that you could fit every single planet in our solar system side by side inside that gap. Jupiter, Saturn, Uranus, Neptune, Mercury, Venus, and Mars could all line up together between us and the moon, with room to spare. When we expand our view to look at the gas giants, the Earth begins to look genuinely tiny. Take Jupiter, the undisputed king of our planetary system. Jupiter is so incredibly enormous that more than 1,300,000 Earths could fit comfortably inside its massive volume. If Earth were the size of a small marble, Jupiter would be the size of a large basketball. The famous Great Red Spot on Jupiter, a massive swirling storm that has been raging for hundreds of years, is actually wide enough to swallow our entire planet whole without even noticing. Then there is Saturn, with its magnificent wide-reaching ring system. Saturn is only slightly smaller than Jupiter, but its rings span a distance that makes our world look like a speck. If you placed Earth next to those rings, it would look like a tiny bead dropped next to a massive, elegant vinyl record. The sheer scale of these gas worlds is enough to make human history feel insignificant, yet they are still just tiny planets orbiting a much more dominant force. They are bound to the gravity of something far grander. That force is our Sun, a star that completely redefines what we mean by the word big. The Sun contains about 99.8% of all the mass in the entire solar system. It is a monstrous, glowing ball of hot plasma that could hold roughly 1.3 million Earths inside its core. To put that into perspective, if the Sun were the size of a typical beach ball, the Earth would be a tiny grain of sand sitting several yards away. The loops of plasma that erupt from the Sun's surface, known as solar prominences, routinely arch out into space at heights that are many times the total diameter of the Earth. The Sun is a nuclear furnace of unimaginable power, fusing millions of tons of hydrogen into helium every single second. The energy it releases keeps our planet warm and allows life to thrive, but it also serves as a stark reminder of our vulnerability. We are completely dependent on this giant cosmic engine, which treats our planet like a minor detail in its vast domain. Yet, as massive as the Sun is, it is critical to realize that our Sun is actually considered a relatively small, yellow dwarf star when compared to the other stars out there. When we look beyond our own solar system, we encounter stars that make our Sun look like a pinpoint of light. Consider a star like Sirius, which is the brightest star in our night sky. Sirius is about twice as massive as our Sun and significantly larger in volume, but even Sirius is dwarfed by hypergiant stars like Betelgeuse, a massive red supergiant located in the constellation of Orion. Betelgeuse is so massive that if you placed it in the center of our solar system where the Sun is, it would swallow up Mercury, Venus, Earth, Mars, and would extend all the way out past the orbit of Jupiter. Think about that for a moment. A single star so colossally large that it would engulf the inner solar system entirely, erasing the very path our planet takes through space. And yet, Betelgeuse is not even the largest star we have discovered. Monsters like UY Scuti and Stephenson 2.18 push the limits of stellar size to an extreme degree. Stephenson 2.18 is roughly 2,150 times the diameter of our Sun. If you wanted to fly an airplane around its circumference at normal cruising speed, the journey would take you hundreds of years to complete. Our Sun is reduced to an invisible speck when compared to these hypergiants, which are themselves just tiny dots within the massive structure of the Milky Way galaxy. The scale of space is not just about the size of objects, but also about the immense, terrifying gaps of nothingness that separate them. The distances between stars are so mind-bogglingly vast that measuring them in miles or kilometers becomes completely useless. Instead, we have to use the speed of light as our cosmic ruler, which travels at an incredible 186,000 miles per second. Light can travel around the entire Earth 7 times in just one single second. It takes about 1.3 seconds for light to travel from the Moon to the Earth. When you look at the Moon, you are seeing it as it existed a little over a second ago. The Sun is much further away, sitting at a distance of about 93 million miles. It takes the light about 8 minutes and 20 seconds to cross that distance and reach our eyes. If the Sun were to suddenly stop shining right now, we would not know about it for over 8 minutes. As we move outward toward the edge of our solar system, these time delays grow significantly longer. Light takes about 4.5 hours to travel from the Sun all the way out to Neptune, the outermost official planet. Think about human space exploration in this context. The Voyager 1 spacecraft, launched back in 1977, has been screaming through space at speeds of over 38,000 miles per hour for decades. It has travelled farther from Earth than any other human-made object in history, crossing out of the immediate bubble of our Sun. Yet, despite travelling for nearly half a century at those incredible speeds, Voyager 1 is only about 22 light hours away from Earth. A radio signal travelling at the absolute speed limit of the universe takes less than a single day to reach it from Earth. On a cosmic scale, Voyager 1 has barely even dipped its toes into the vast ocean of interstellar space. It would take the spacecraft tens of thousands of years to reach the nearest neighbouring star system if it were heading in that direction. That closest neighbouring star system is Alpha Centauri, which sits about 4.4 light years away from us. This means that when we look at the closest stars to our Sun, we are seeing light that left them over 4 years ago. The space between our Sun and Alpha Centauri is not filled with planets or structures. It is an incredibly vast, cold, and empty void. There is almost nothing out there but a few stray atoms and cosmic dust. This immense isolation is the defining characteristic of our universe. When you realize that the nearest star is over 4 light years away, you begin to see how spread out the galaxy truly is. Now, imagine a structure that contains not just 1 or 2 stars, but hundreds of billions of them, all bound together by gravity. That structure is our galaxy, the Milky Way. The Milky Way is a massive, swirling spiral disk of stars, gas, and dust that stretches across an incomprehensible distance of roughly 100,000 light-years from one edge to the other. If you wanted to cross our galaxy from side to side, travelling at the speed of light, it would take you a full 100,000 years. Human civilization has only existed for a fraction of that time. Our Sun is located about 26,000 light-years away from the centre of the galaxy, sitting quietly in one of the spiral arms known as the Orion Arm. We are out in the galactic suburbs, far away from the crowded, energetic core where a supermassive black hole resides. Every single star you can see with the naked eye in the night sky is just a tiny part of our local stellar neighbourhood. When you look up on a clear night and see thousands of twinkling lights, you are only seeing a tiny fraction of the Milky Way. It is like standing in your front yard and looking at the nearest few houses, completely unaware of the massive metropolis that extends for miles all around you. The galaxy contains anywhere from 100 billion to 400 billion stars, and most of those stars likely host their own systems of planets. The sheer quantity of worlds out there is staggering, yet the Milky Way itself is just a single member of a small collection of galaxies known as the local group. The local group spans a distance of about 10 million light-years and contains a few dozen galaxies, with the Milky Way and the Andromeda Galaxy being the two largest and most dominant members. Andromeda is currently located about 2.5 million light-years away from us, making it the most distant object you can see with the naked eye under perfect dark skies. When you look at the Andromeda Galaxy in the night sky, you are looking at an object that contains an estimated 1 trillion stars. It is an immense island of light, even larger than our own Milky Way, drifting through the deep cosmos. Right now, a cosmic drama of epic proportions is unfolding. The Andromeda Galaxy and our Milky Way are hurtling toward each other at a speed of about 70 miles per second. Over the next several billion years, this gap will close completely, and these two massive stellar systems will collide and merge into a single, giant, elliptical galaxy. Despite the word collision, the spaces between individual stars are so immense that almost no two stars will actually hit each other directly. Instead, they will pass right through like ghosts, their gravitational forces pulling and stretching great streams of gas and stars across the void. It is a slow, majestic dance that will reshape our entire night sky over eons. Yet even this massive local interaction is just a microscopic event happening within a much larger structure. The local group, which feels so incredibly vast to us, is merely a tiny outer branch of an even greater cosmic network. If we zoom out even further, the local group reveals itself to be just a small component of the Virgo supercluster. A supercluster is a massive collection of galaxy groups and clusters bound together by gravity, forming the large-scale structure of the universe. The Virgo supercluster stretches across an incomprehensible distance of 110 million light-years and contains at least 100 galaxy groups and clusters. Within this structure, our home galaxy is reduced to a tiny, unrecognizable dot, completely lost among thousands of other islands of stars. But the scale does not stop there, because the Virgo supercluster itself is just a minor appendage of an even larger entity discovered by astronomers, known as Laniakea. In the Hawaiian language, Laniakea translates to immeasurable heaven, a deeply fitting name for a structure that spans 520 million light-years from end to end. Laniakea contains roughly 100,000 galaxies, all flowing along cosmic rivers of gravity toward a central point known as the Great Attractor. Looking at a map of Laniakea is like looking at a delicate, glowing nervous system, where entire galaxies are just individual cells. At this level of reality, human concepts of direction, distance, and time completely lose meaning. We are looking at a cosmic web where the largest structures imaginable are woven out of threads of light, and each light is a galaxy containing hundreds of billions of suns. Yet, incredibly, Laniakea is still just one of millions of superclusters that exist within the observable universe. The observable universe is the sphere of space that human beings can theoretically see from Earth, limited only by the speed of light and the age of the cosmos. Because the universe is roughly 13.8 billion years old, you might assume that the observable universe extends 13.8 billion light years in every direction. However, because space itself has been expanding ever since the Big Bang, the edge of the observable universe has pushed out much further. The actual diameter of this observable sphere is a staggering 93 billion light years. Within this bubble, there are estimated to be at least 2 trillion individual galaxies, each teeming with stars, planets, and moons. Try to hold that number in your mind. 2 trillion galaxies. If you were to count every grain of sand on every beach and desert across the entire Earth, that total number would still be dwarfed by the estimated number of stars in the observable universe. We are talking about a reality so immense that it defies the capacity of the human brain to truly comprehend it. Every single person who ever lived, every empire that rose and fell, every thought ever recorded, occurred on a planet that is less than a grain of sand in a cosmic desert. The sheer scale of this emptiness can make human existence feel completely meaningless, a brief flash of biological activity on a lonely rock. But there is another side to this perspective. The universe is not just incredibly large, it is also governed by physical laws that limit our ability to ever truly explore it. The cosmic speed limit, the speed of light, acts as a hard boundary that seals us off from the rest of the cosmos. Even if we could somehow build a spacecraft that travels at the speed of light, it would still take us millions of years just to leave our local cosmic neighborhood. Furthermore, because the expansion of the universe is accelerating, the distant galaxies we see today are moving away from us faster and faster. Eventually, they will move away faster than the speed of light itself, meaning their light will never be able to reach us again. They will fade from our view forever, slipping over the cosmic horizon into total invisibility. We are living in a unique window of time where we can still see these distant structures and map our place among them. When we consider the concept of time dilation, the universe becomes even stranger. According to Einstein's theory of relativity, as an object moves faster through space, time moves slower for it relative to an observer who is standing still. If astronauts were to board a highly advanced starship that could travel at 99% the speed of light, their journey across the galaxy would take thousands of years from the perspective of the people left behind on Earth. However, for the astronauts inside the ship, the journey would feel like it took only a few decades due to time dilation. They could theoretically travel deep into the cosmos, but if they ever decided to return home, they would find that millions of years had passed on Earth. Everyone they knew would be long gone, human civilization might be entirely extinct, and the planet itself would have aged beyond recognition. Travelling across the stars is a one-way trip through time, a complete severing of ties with the world of your birth. The physical laws of our universe seem designed to keep star systems isolated from one another. This realization brings us to a profound question. Are we truly alone in this immense sea of space? With trillions of galaxies and uncounted trillions of planets, the mathematical probability of alien life seems incredibly high. Yet we have found absolutely no evidence of anyone else out there. This contradiction is known as the Fermi paradox. If the universe is so old and so massive, filled with countless places where life could evolve, where is everybody? Why is the cosmic silence so deafening? One possible explanation is the sheer, brutal factor of distance. Even if there are thousands of advanced alien civilizations scattered across the Milky Way right now, they might be separated by thousands of light years of empty space. Their radio signals would take millennia to reach us, weakening into background noise along the way. They might look out at our solar system and see the Earth as it was during the Ice Age, completely unaware that an industrial civilization has recently emerged here. Another sobering thought is the concept of the Great Filter. This theory suggests that there is a highly difficult barrier that life must cross to become an interstellar civilization, and almost all life fails to get past it. This filter could lie in our past, such as the incredibly rare leap from simple, single-celled organisms to complex multi-celled life. Or, more terrifyingly, the Great Filter could lie in our future, meaning that civilizations naturally tend to destroy themselves through war, climate collapse, or technological catastrophe shortly after discovering advanced physics. As we ponder these ideas, we have to look back at our own solar system to understand the sheer hostility of space. Our planetary neighbours are beautiful, but they are also environmental nightmares compared to Earth. Venus, which is roughly the same size as Earth, is a runaway greenhouse world where the surface temperature is hot enough to melt lead, and the atmospheric pressure is equivalent to being a half-mile deep in Earth's ocean. It is a choked, sulfuric, acid-rained hellscape. Mars, our other close neighbour, is a frozen desert with an atmosphere so thin that your blood would boil at body temperature without a pressurized suit. It is bombarded by solar radiation and swept by massive dust storms that can wrap around the entire planet for months at a time. The gas worlds of Jupiter and Saturn lack any solid surface to stand on. They are fluid oceans of hydrogen crushed by gravity so intense that it would flatten any human vehicle in an instant. To fully grasp the architecture of our local space, we must look closely at how the cosmic neighborhood is organized. The Milky Way does not float alone in the deep vacuum. It belongs to a structural family known to astronomers as the local group. This collection of galaxies spans a distance of roughly 10 million light-years, forming a small island of matter bound together by mutual gravity within the expanding universe. Within this group, there are more than 50 companion galaxies, but the vast majority of them are dwarf systems, small, irregular, or elliptical collections of stars that lack the grand scale of our home spiral. These smaller systems, like the large and small Magellanic Clouds that visible from Earth's southern hemisphere, are captured by the immense gravity of the larger members. They drift in permanent orbit around their massive neighbours, destined to eventually be torn apart and absorbed. Their stars scattered into the halo of whichever giant galaxy claim them within this local group. The Milky Way and Andromeda dominate everything. Together, they account for the overwhelming majority of the group's total mass and stellar population. They are the gravitational kings of this particular cosmic neighborhood, and every smaller galaxy within 10 million light-years exists under their combined influence. But these two kings are not sitting still. They are not maintaining a polite distance from one another across a quiet cosmic suburb. The Milky Way and Andromeda are separated by approximately 2.5 million light-years of intergalactic space. That distance is enormous by any human standard. It represents a gulf so vast that light itself, travelling at the ultimate speed limit of 186,000 miles per second, requires 2.5 million years to complete the crossing. When you look into the night sky toward the constellation of Andromeda, you are seeing that galaxy as it was when early hominids were first walking the plains of Africa, long before modern humans evolved. The photons striking your retina have been travelling through the deep vacuum of intergalactic space for millions of years, just to end their journey on your eye. Yet, on the scale of the universe, this immense distance is actually a tight embrace. The two galaxies are so close that their mutual gravitational attraction is actively overcoming the general expansion of the universe. While more distant galaxies are being pushed away from us by the mysterious force of dark energy, Andromeda is falling toward the Milky Way. The implications of this approach, the timeline, the geometry, the physics of what happens when they meet, and the fierce ongoing scientific debate about the precise nature of that meeting, form the core of the next chapter of this story. Because the distance between the Milky Way and Andromeda is not merely a number, it is a physical space so vast that it breaks every intuitive framework the human brain has for understanding separation. It is a gap so extreme that translating it into any unit of measurement a person can visualize produces results that stop functioning as meaningful descriptions of distance and start functioning as evidence that the universe was not designed for human comprehension. Every analogy fails. Every comparison collapses under the weight of the actual figures. And what is moving across that distance? It is not a single particle or a small vehicle, but two entire stellar empires, containing more than 1 trillion suns combined. Let us try to scale this down to something our minds can attempt to hold. We measured our own solar system and found it incredibly large, spanning billions of miles out to Neptune and trillions more out into the Oort cloud. We looked at Voyager 1 and saw that after nearly 50 years of continuous flight at 38,000 miles per hour, it had covered 15 billion miles. a distance that feels massive by any terrestrial standard, but remains invisible within the Milky Way. We measured the Milky Way and found it incomprehensibly large, containing hundreds of billions of stars across 100,000 light-years of space. And then we discovered that the galaxy next door, Andromeda, is more than twice the diameter of our home, contains up to 1 trillion stars, and possesses a central black hole 25 times more massive than ours. Each step on this journey has demolished the sense of scale established by the previous step. Each level of cosmic organization has made the last one disappear. Now we confront the gap between them, and this is where the numbers stop behaving like numbers. This is where the human brain, which evolved to track the distance between a predator and a watering hole, reaches a wall it cannot climb. Let us start with the light year, our baseline cosmic ruler. 1 light year is roughly 5.88 trillion miles. That is the distance light travels in a single year through a vacuum. To walk a single light year at a normal human pace of 3 miles per hour would take you about 200 billion years, a time span over 14 times longer than the age of the universe itself. Even our fastest machines are completely helpless against this scale. Consider the Apollo missions to the moon, every crewed space mission in human history, every walk on the lunar surface, every orbit of the Earth, every spacewalk conducted from the International Space Station, all of it combined does not begin to approach 1 light year of distance. Now multiply that figure by 2.5 million. The distance to the Andromeda galaxy is approximately 2.5 million light years, which translates to roughly 14.7 quadrillion miles. Write it out. A 14 followed by 15 zeros. It is a number that means absolutely nothing to a human being. It is a mathematical abstraction, a clean symbol on a page that masks a terrifying abyss of absolute nothingness. If you wanted to build a scale model where the Earth was a microscopic speck invisible to the naked eye, and the Sun was the size of a grain of sand, the distance to Andromeda would still require a map that stretches across continents. The space between these two galaxies is so empty that it makes the void of our solar system look crowded. In the space between stars within a galaxy, there is a thin mist of gas and dust, the interstellar medium. But in the space between galaxies, even that thin mist vanishes almost completely. This is the intergalactic void, a place where matter density drops to just a few stray hydrogen atoms per cubic meter. It is a cold, dark, silent desert where nothing has happened for billions of years, and nothing will happen until these two massive systems complete their multi-billion-year drop toward one another. The acceleration is constant. Right now, as you read these words, Andromeda is getting closer. It is pulling the Milky Way toward it, and the Milky Way is pulling Andromeda in return. They are falling into a gravitational well that they are creating together. The speed of their approach, roughly 70 miles per second, means that every single hour, the distance between our home and Andromeda shrinks by about 250,000 miles. That is nearly the entire distance from the Earth to the Moon, erased every single hour of every single day. Yet, because the total distance separating them is 14.7 quadrillion miles, this rapid approach looks like total stillness on a human timescale. If you look at Andromeda through a telescope tonight and then look at it again next year, or a century from now, it will look exactly the same. Its size in the sky will not change by a fraction of a millimeter. To see any visible alteration in the structure of the sky, you would need to live for millions of years. This is the ultimate disconnect of the cosmos. Events of catastrophic scale and immense velocity are smoothed out by the sheer enormity of space until they look like eternal frozen monuments. The sky appears permanent, a reliable canvas of fixed stars, only because our lifetimes are too short to notice the continental drift of the galaxies. The traditional understanding of the upcoming interaction between our galaxy and its massive neighbour has always been straightforward and clean. For generations, the prevailing consensus across textbooks, planetarium shows, popular science journals, and television documentaries has outlined a highly dramatic, inevitable, head-on collision. According to this classic model, The two enormous stellar systems are on a direct, unswerving path toward one another and will experience a monumental impact in approximately 4 to 4.5 billion years. The cosmic merger is predicted to fuse them entirely, reorganizing the chaotic aftermath into a single, highly stable, and massive elliptical galaxy. It stands as one of the most famous standard facts in the entire field of popular astronomy, widely shared and accepted as absolute certainty by the general public. However, the real cosmic picture is significantly more nuanced and complex than these simplified public narratives suggest. Over the past decade, the advanced astrophysics community has seen its core understanding evolve in deep and unexpected ways. Scientists have long possessed highly accurate, verified data regarding the direct radial velocity of the Andromeda galaxy. We know with absolute certainty that the physical gap along the line of sight between our system and Andromeda is closing at a relentless pace of approximately 110 kilometers per second. This specific figure has been repeatedly tested, calculated, and confirmed by numerous independent astrometric investigations over many years. Yet relying solely on radial velocity provides an incomplete story because it measures motion in only a single dimension. It tracks how quickly the distance between the two objects shrinks along a perfectly straight line drawn between their centers. What it completely fails to reveal is the transverse velocity, which is the sideways drift of Andromeda relative to the Milky Way. Measuring how much a galaxy slips to the left or right across millions of light years is an extraordinarily challenging astrometric task that requires observing the microscopic movements of individual stars against the backdrop of incredibly distant cosmic objects like quasars. This critical data gap was finally bridged by advanced modern observatories, particularly through the revolutionary data sets provided by Europe's Gaia Space Telescope. In studies published around 2019, utilizing Gaia's highly detailed data release 2, astronomers succeeded in producing the very first truly robust, verified calculations of Andromeda's transverse velocity. The sophisticated measurements revealed that Andromeda possesses a sideways motion of roughly 57 kilometers per second. Because tracking these movements across such an immense intergalactic gulf is prone to minor errors, scientists include a realistic margin of uncertainty, placing the actual sideways velocity somewhere within a range of 40 to 70 kilometers per second. This discovery completely changes how we view the impending encounter. A sideways motion of 57 kilometers per second is far from minor. It introduces a massive variable into the gravitational math. It means the two galaxies are absolutely not traveling toward each other along a perfectly neat, simple straight line. Instead, their orbital trajectory involves a highly distinct, cross-directional trajectory offset. This sideways component injects a profound level of genuine scientific uncertainty into the classic timeline, introducing several highly complex possibilities for how the structural mechanics will play out. The presence of a substantial transverse velocity makes a direct central head-on smash on the very first orbital pass highly improbable. Rather than a sudden dramatic plunge, it is vastly more likely that the two systems will experience a glancing initial pass. Instead of one quick, singular impact event, the galaxies will execute a beautiful, terrifying cosmic flyby. They will graze each other's outer galactic halos, swinging past one another before their mutual gravitational fields inevitably slow them down, halt their outward momentum, and pull them back together for subsequent passes. This orbital complexity heavily warps the anticipated cosmic calendar. Depending on the precise geometric parameters of their paths, the ultimate timeline for the final merger stretches considerably. It pushes the expected date of full coalescence out from the traditional 4.5 billion years to 5 billion, 6 billion, or potentially even closer to 10 billion years into the deep future. Current computer models indicate that while the initial close encounter and grazing swipe will likely occur in about 4.5 billion years, the intricate dance required to fully blend the two systems into a singular structure might take up to 8 or 10 billion years to fully conclude. To maintain absolute scientific clarity, it is vital to distinguish between what is actively debated and what remains undisputed within the international astrophysics community. There is absolutely no debate surrounding the fact that the Milky Way and the Andromeda Galaxy are gravitationally trapped by each other and are closing the distance between them. The observed radial blue shift is an empirical reality. The profound gravitational pull they exert on one another is a verified fact, and a massive structural disruption will absolutely take place. What remains under vigorous scientific investigation is solely the precise geometric path of the encounter, the exact time frame of the initial close pass, and the fluid dynamics of the merging gas clouds. Let us step away from the mathematical debates regarding timing and geometry to explore a far more fundamental concept. What does a full-scale galactic merger actually look like in physical reality? In the popular imagination, fueled by sci-fi movies and loose terminology, the word collision conjures terrifying visions of catastrophic planetary ruin, exploding stars, widespread atomic fireballs, and instant destruction across solar systems. Yet this spectacular mental image is almost entirely false. A galactic merger operates on principles that bear no resemblance to a collision in any sense that a human being would intuitively recognize. During this monumental event, stars will not physically crash into one another. The reason for this complete lack of physical contact traces back directly to the profound, overwhelming cosmic emptiness that defines galactic structures. Individual stars inside galaxies are separated by distances that are completely staggering when compared to their actual physical sizes. Within our local stellar neighborhood, the average distance separating any single star from its nearest companion hovers between 4 and 5 light years. While a star itself might measure a few 100,000 or a few million miles across, the immense gulf of nothingness separating them spans tens of trillions of miles. Because the voids are so incredibly vast, and the physical targets are so small, the stars from Andromeda will slide smoothly through the interstellar spaces of the Milky Way, like ghosts sliding through an empty mansion. The mathematical probability of two individual stars directly impacting each other over the course of the multi-billion-year merger is so close to zero that it is functionally negligible. Instead of physical contact, the primary force driving the merger is gravity. As the two massive systems pass through and around one another, their immense collective gravitational fields will generate titanic tidal forces that stretch across thousands of light years. These tidal forces do not need to bring single stars into physical contact to completely rewrite the architecture of both galaxies. Gravity will violently warp stable orbits, tear apart spiral arms, and fling billions of stars into entirely new trajectories. Some stars will be slung outward on immensely long, looping paths into the cold intergalactic void, while others will be drawn violently downward into the rapidly consolidating galactic core. The neat, highly organized, and beautiful spiral patterns that currently define both the Milky Way and Andromeda will be progressively stretched, twisted, and permanently ruined. Over hundreds of millions of years following the initial grazing pass, the elegant spiral arms will dissolve entirely into chaotic, unstructured streams and massive shells of drifting stars. The orderly, flattened galactic disks will lose their structure, puffing up into a much rounder, less organized, and randomized shape. Meanwhile, the immense reservoirs of interstellar gas scattered within both galaxies will react in a completely different manner than the stars. Because stars are highly compact and widely separated, they pass through without touching. Gas clouds, however, are vast, diffuse, and continuous structures. When the gargantuan hydrogen gas clouds of the Milky Way smash into the gas clouds of Andromeda, they will not pass through like ghosts. Instead, they will slam into each other with immense force, creating powerful hydrodynamic shocks and compression waves. This widespread cosmic compression will trigger a massive rapid collapse of the gas, sparking an era of intense hyper-accelerated star formation known to astronomers as a starburst. Across the interacting systems, millions of brilliant short-lived blue stars will ignite simultaneously, illuminating the distorted shapes of the merging galaxies in a brilliant display of cosmic rebirth. We do not have to rely solely on theoretical calculations or computer simulations to visualize this process. The universe has left real examples scattered across the night sky, acting as a living gallery of our own future. When we train our most powerful telescopes on distant deep space objects, we can observe galaxies frozen at various stages of this exact structural transition. Look at the antennae galaxies, located roughly 60 million light-years away. They are a pair of major spiral systems caught in the ferocious middle stages of a major gravitational merger, their ancient structures completely disrupted, with long, delicate tidal tails of stars streaming out into space like paths of wreckage from a slow-motion car crash. Consider the Cartwheel Galaxy, situated approximately 100 million light-years from Earth, which reveals an even rarer and more violent geometric interaction. It forms a brilliant ring-like structure that occurred when a smaller satellite galaxy punched straight through the bullseye center of a larger spiral disk at immense speed. The high-velocity impact sent a massive shockwave of compressed gas radiating outward across the entire galaxy, triggering a colossal ring of new star formation like a ripple spreading outward across the smooth surface of a pond. The culprit galaxy passed completely through and remains clearly visible nearby, leaving behind a magnificent stellar structure unlike anything in our local cosmic neighborhood. These real-world examples confirm the mechanics of our future. After the intense starburst era peaks and consumes the vast majority of the available hydrogen fuel, star formation will experience a sharp, permanent decline, and the merged system will begin to quiet down. The ultimate configuration, reached roughly 1 to 2 billion years after their final central coalescence, will be a colossal, featureless, elliptical galaxy. There will be no elegant spiral arms left, no flattened dusty disk, but rather a massive, elongated blob of trillions of ancient stars, orbiting a single common center of mass in completely randomized directions. Astronomers have playfully proposed several names for this future merged giant, including Milkomeda or Milkdromeda. While the names sound light-hearted, the physical structure they describe is absolutely immense. This combined system will host anywhere between 1.5 to 2 trillion individual stars, with a collective mass exceeding 2 trillion solar masses. The core of Milkdromeda will be completely dominated by the merger of their respective central black holes. Sagittarius AI and Andromeda's massive 100 million solar mass black hole will slowly spiral toward one another, eventually fusing in a cataclysmic event that will release an unbelievable torrent of gravitational waves across the fabric of the universe. Where does our own solar system fit into this chaotic reorganization? Detailed orbital simulations show that our Sun and its planets will almost certainly survive the merger intact, completely shielded by the immense emptiness of space. However, our position within the galactic map will be completely rewritten. There is a high statistical probability that our solar system will be pushed much farther out into the new galaxy's outer halo, resting at a significantly greater distance from the core than it does today. Conversely, we could be pulled inward toward the energetic center. In a small percentage of simulations, our Sun is even ejected entirely, becoming an unbound rogue star drifting through the intergalactic void with no galactic home. From the perspective of any hypothetical observers living on Earth billions of years from now, these radical structural shifts would be completely unnoticeable on a human timescale. Because galactic mergers unfold across hundreds of millions of years, the night sky will alter with extreme, imperceptible slowness over generations. Over millennia, unfamiliar stars arriving from Andromeda will gradually blend into our local night sky, slowly distorting our traditional constellations completely beyond recognition. The familiar bright band of the Milky Way will warp, growing intensely bright in regions of starburst activity and dimming in others, before slowly dissolving over eons into a completely smooth, uniform glow spanning the entire sky. To understand the deeper significance of these gargantuan movements, we must confront the absolute physical limitations built into the very core of our universe. The vast gaps separating galaxies like the Milky Way and Andromeda are not merely obstacles that a highly advanced future civilization might overcome with enough engineering skill and patience. Instead, they represent fundamental, unyielding horizons dictated by the laws of relativistic physics. When we examine the possibility of traveling between these stellar systems, We run directly into an absolute wall of cosmic speed limits and energy requirements that make intergalactic journeys virtually impossible, no matter how many millions of years a society has to develop technology. The ultimate speed limit of reality, as discovered by Albert Einstein, is the speed of light in a vacuum, 186,000 miles per second. This is not a mechanical limitation of our current engines. It is a fundamental property of space-time itself. As any object possessing mass accelerates closer and closer to this cosmic speed limit, its relativistic mass increases toward infinity. Consequently, the amount of energy required to accelerate that object even a fraction of a percent faster begins to climb exponentially. To push even a small, modest spacecraft up to the speed of light would require an infinite amount of energy, more energy than exists across the entire observable universe. Because of this unyielding physical barrier, any physical journey across the intergalactic void must always proceed at a velocity strictly below this ultimate threshold. Now, consider the practical implications of this rule when applied to the distance between the Milky Way and Andromeda. As we established, that distance stands at an incredible 2.5 million light-years. This means that even if a future civilization could somehow construct a starship capable of traveling at 99.9% the speed of light, the journey from our galaxy to Andromeda would still consume more than 2.5 million years from the perspective of observers remaining behind on the homeworld. Entire species could evolve, civilizations could rise and fall into absolute dust, and continents could drift across the surface of the Earth during the time it takes for that single vessel to complete its crossing through the deep intergalactic void. This introduces the profound phenomenon of time dilation, which warps our traditional understanding of time and travel in an extraordinary way. According to special relativity, time does not flow at a uniform rate throughout the universe. It is completely relative to the velocity of the observer. For the bold astronauts aboard a vessel traveling at extreme relativistic speeds, time would slow down dramatically compared to the time passing back on Earth. If the ship were moving fast enough, the 2.5 million year journey across the intergalactic gulf might feel like only a few decades to the crew inside the cabin. They could eat their meals, sleep in their quarters, and live out their normal adult lives, surviving to see the magnificent structure of Andromeda loom large outside their viewing ports. Yet this distortion of time comes at a devastating emotional and societal cost. It represents a total, irreversible severance from the world of their birth. If those astronauts were to complete their mission, explore the alien star systems of Andromeda, and then turn their ship around to make the long journey back to the Milky Way, they would return to a home galaxy that had aged by 5 million years. The planet Earth they left behind would be completely unrecognizable. The human race would likely be long extinct, the sun would be significantly older and brighter, and every trace of the civilization that built their spacecraft would have vanished from the archaeological record. Intergalactic travel at relativistic speeds is essentially a one-way trip into the extreme future, a complete exile from everything the travelers ever knew. Furthermore, we must look at the physical environment of the intergalactic medium that these travelers would have to cross. The space between the Milky Way and Andromeda is often described as an absolute vacuum, but it contains hidden dangers that become catastrophic when moving at relativistic velocities. Even though there are only a few stray hydrogen atoms and microscopic dust particles per cubic meter in that deep void, a spacecraft traveling at nearly the speed of light would experience these stationary particles as a relentless torrent of highly destructive, high-energy cosmic radiation. Every single isolated atom striking the front of the ship would hit with the kinetic energy of a high-velocity particle accelerator, slowly eroding the hull and threatening to fry the electronic systems and biological tissue inside. To survive such a crossing, a vessel would need shielding of an unimaginable scale, perhaps magnetic fields of immense power or physical barriers miles thick, adding colossal mass to a ship that already requires infinite energy to accelerate. The engineering problems quickly compound until they slide out of the realm of practical physics and into the realm of mathematical absurdity. This reveals a profound truth about our place in the cosmos. The universe is structured in a way that creates natural quarantine zones. Galaxies are essentially immense, isolated islands of matter, separated by oceans of nothingness so deep and hostile that they function as permanent geographic borders. We are allowed to look across the water, but we are strictly forbidden from crossing it. This absolute isolation forces us to re-examine our understanding of cosmic loneliness and the distribution of life across space and time. If the laws of physics permanently confine civilizations to their home galaxies, then the search for intelligent life changes completely. Even if the universe is absolutely teeming with advanced technological societies, they are all trapped inside their own galactic bubbles. A civilization flourishing in the Andromeda galaxy could build magnificent works of planetary engineering, harness the energy of their central supermassive black hole, and map every corner of their trillion-star empire, yet we would never know they exist. Their radio transmissions, weakening and spreading out across the 2.5 million light-year gulf, would dissolve into completely undetectable background noise long before reaching our antennas. This realization sheds a new sobering light on the Fermi paradox, which asks why we have never found any physical evidence of alien intelligence despite the immense age and size of the cosmos. The answer may not be that life is incredibly rare, or that advanced civilizations always destroy themselves, but simply that the distances are too great and the physics are too strict. The universe does not allow for a grand, interconnected, intergalactic community. It is a reality composed of completely isolated stories, where every galaxy is a closed book, containing histories, cultures, and biological epics that will never communicate with or influence the stories unfolding anywhere else. As we look out into the night sky, seeing the faint smudge of the Andromeda galaxy drifting among the stars, we are looking at an entirely independent universe of possibilities that is forever beyond our reach. We are observing 1 trillion suns that we can calculate, model, and photograph with extraordinary precision, but whose physical surfaces no human foot will ever touch. This duality is one of the most poignant aspects of the human condition. The universe has given us an intelligence capable of understanding the true scale of cosmic reality, yet it has placed us inside a fragile biological frame, stuck on a tiny rock and bound by absolute laws of physics that ensure we can see the grand stage but never step out onto it. To fully grasp our place in this vast reality, we must shift our attention back down from the giant superclusters and look closely at the very tool we use to perceive all of this grandeur. The ultimate realization of cosmology is not just that the universe is unbelievably vast, but that a tiny fragment of the universe has developed the ability to think, calculate, and look back at itself. We exist as an extraordinarily rare occurrence, conscious matter that can map the very emptiness that threatens to make us feel entirely meaningless. The cosmic scale is undeniably terrifying, yet the fact that we can measure it at all is perhaps the most stunning detail of the entire story. Think about the physical mechanism that is currently processing this information. You possess a brain that weighs only about 3 pounds, consisting of a delicate network of neural tissue. This organic structure operates on an incredibly tiny amount of energy, running on the caloric equivalent of a dim, flickering light bulb. For hundreds of thousands of years, this specific biological organ evolved under very practical, terrestrial constraints. It was structurally optimized by nature for simple, immediate survival tasks, such as tracking antelopes across the wide-open African savanna, finding freshwater sources, and avoiding local predators. It was never designed by evolution to understand the vast mechanics of quantum physics, or to calculate the immense distances separating superclusters across the cosmic web. Yet, despite these incredibly humble origins and major biological limits, this tiny 3-pound organ has managed to break free from its local constraints. By combining basic mathematics, systematic observation, and logical reasoning, human beings have managed to reach far out into the deep void from the surface of our tiny world. We can sit quietly in a small room, look through a glass telescope, write out lines of equations on a simple piece of paper, and accurately map structures that are so monstrously large that a beam of light would require billions of years just to cross them. We have successfully calculated the precise weight of invisible black holes, discovered the chemical composition of stars burning trillions of miles away, and reconstructed the history of the cosmos, all the way back to the initial moment of the Big Bang. This creates an extraordinary, beautiful paradox at the center of human existence. On one hand, the absolute terrifying truth is that we are physically small enough to be permanently trapped inside a single, isolated galaxy among trillions of other unreachable systems. We live out our brief, minor lives for roughly 80 years on a planet that measures only about 7,900 miles in diameter, completely bound by strict physical laws that forbid us from ever physically crossing the deep intergalactic ocean. We are a microscopic flash of biological activity happening on a lonely rock that is entirely lost in an indifferent, endless desert of empty space. On the other hand, we are intellectually capable enough to measure the massive galaxy sitting right next door with absolute extraordinary precision. We can actively see exactly what we cannot physically reach, and we can mathematically calculate exactly what we are forbidden from ever crossing. Our bodies are confined to a tiny grain of sand, but our minds can encompass the entire observable universe. We are the universe's way of thinking about itself, a rare spark of conscious awareness illuminating the deep cosmic dark. When you brace yourself against the crushing scale of our size in the cosmos, remember that the very mind feeling small is the grand thing capable of holding the entire universe within its thoughts.